Good afternoon. My name is Olivier Gourgue from University of Antwerp. The interaction between plants and flow is really important to attenuate the flood propagation. In this very simple Lego experiment, we can see 6 little guys standing up, waiting for the storm. And during the storm, the big waves coming from the top, they are propagating inland. And as you can see, the propagation is more important in the area where there is no vegetation. So that at the end, only the 3 little guys protected by vegetation are still standing up. This is because vegetation increases the friction on the flow and therefore attenuate the flood propagation. This is something that is actually easy to simulate in this case because vegetation is very dense and quite homogeneously distributed. But in reality, it is much more complex. The coastal vegetation presents much more diverse fine-scale structures. And in general, large-scale models that are used to predict flood propagation, they are missing those fine-scale structures because they are too coarse. And in the next few slides, I'm going to show that it matters. So on the right, we have a simulation of flow through a vegetation box. The small black box, the big black box, sorry, represents more or less a grid cell on this figure. And within that black box, we have a random distribution of vegetation, the small white cells. So the flow is coming from the top, going through vegetation. It is attenuating through the vegetation and deviating on the side. On the left graph, I show you the discharge through the vegetation patch. And we consider for a given biomass within the big box, I show you different degree of clustering of vegetation. And what this graph shows is that the vegetation clustering, it decreases the flow attenuation. This is because for a given biomass, if the vegetation is clustered, the flow can find more easily a way through the vegetation patch. So now coming back to our large-scale model, we want to attribute a single friction value to the big black box, right? And usually models, what they do, they are using an approach where they account only for the average biomass, considering that the vegetation is perfectly spread over the box, the vegetation box. And this is a bad idea because, as you can see on this graph, the friction is overestimated and the flow attenuation is overestimated. Okay, so this is something we want to solve, and to do that, we are making an analogy to electronic circuit theory. On the left, you have the famous Ohm's law linking the electric potential to the electric current through the circuit resistance. And on the right, you have the Chesi formula linking the flow potential to flow velocity through the Chesi coefficient, which is a way to quantify the friction or the flow resistance. So now, if we consider all the small vegetation grid cells at the subgrid scale has a resistance with high resistance for vegetation, low resistance for no vegetation. And if we connect those resistors in series along the flow and in parallel across the flow, then we end up with an electronic circuit like on this graph, which is very simple and very simple to determine the total resistance of the circuit. And similarly, the total friction of our vegetation cell. So now if we apply the simple strategy, very cheap, to our case here, we can see that the discharge to the vegetation is much better represented. And that is, good, of course, a good idea, a good novel. And now if we apply this method further to our large-scale models, we are now able to predict flood propagation in coastal areas more accurately. Thank you.